Welcome to this video in the Matter Unit. This is 1.3, where today we are going to learn about all the techniques to separate and purify mixtures. Following this lesson, you should be able to describe the different methods for purification and separation, be able to explain how the methods are similar and differ from one another, and recap how mixtures are formed and how they differ from compounds. So if you haven't already done so, please make sure you got your chemistry notes handy because we're going to be jotting down a lot of great information. And of course, as we always say, if you have questions, make a note of that too, so we can cover that during our burning questions segment. So without any further ado, let's get cooking. So as we begin this lesson, one of the things that I want to remind you of is that mixtures and compounds are fundamentally different. From their formation to the way that they're separated to the way the components either retain or don't retain their properties, they are drastically different from one another. One of the first things you guys need to remember is that mixtures are created by physically blending and by just throwing things together. And compounds, on the other hand, are created by a chemical reaction. As a result of that, if you really wanted to separate a mixture, you can do that by physical processes, and if you wanted to separate a compound, you would have to do that by a chemical means, meaning a chemical reaction. Now, why can you separate a mixture by physical processes, unlike a compound? Well, that's because if there was no chemical reaction required to make it, those components that go into your mixture, therefore, definitively retain all of their original properties. And it is the leveraging of those properties that we will use in the different separation and purification techniques that are contained here in this video. All right, so what I'm going to do is I'm going to choose each different type of separation process and give you the finer points of those and then come back to this master list. So make sure you organize your notes accordingly. The first one I want to jump into is magnetism. Magnetism is pretty cool and pretty self-explanatory if you consider it. You have to use the physical property of something being magnetic and something not being magnetic to be able to separate the mixture. Take, for example, if we wanted to separate sulfur here and iron filings. Well, sulfur is non-magnetic while iron filings are magnetic. So if we were to have a mixture of iron and sulfur, we could very simply take a magnet to pull off the iron particles, and that would give you purified components of both sulfur and iron. So this always works if one of your components is indeed magnetic. So be sure to check that physical property. Back to this. Now we are going to jump into flotation. So flotation, as Jimi Hendrix says, is groovy and relies on the physical property of density. You must have your substances be either more or less dense than each other. Take, in this case, oil and water. Now, you guys know from biology that oil and water don't mix. And you learned about hydrophilic and hydrophobic. Well, you are going to learn the chemistry behind that later this year. But for now, all you have to know is that obviously, if one can float on the other, in this case, the oil can float on the water must be more dense than the oil is. So this is what's called a filter flask. And if you were to take a mixture of oil and water and put it in there and allow density to do its thing and separate out, you can then open up this flask here, let the water out, and then you will be left with just oil in your mixture with probably some small water particles that are still in there. Obviously, if you repeat this a bunch of times, you may be able to refine your technique to get a 99% recovery of oil and water, but it's really hard to completely separate these two components out. Flotation can also be quite effective when you have a solid in a liquid, and that solid is obviously of a different density than your liquid is. Take, in this case, we have rice grains, which are floating on water. So what happens is, because the rice is less dense than the water, you can immediately use your hand or a forceps or any type of tool to go scoop these out and take them away, purifying the mixture. You're left with just the rice components and then the water and then whatever else is inside this water here that has to be dealt with separately, but because this floats, you can use flotation and leverage that property to separate and purify the mixture. Back to this, I really quickly just want to talk about hand separation. You'll notice I don't have a separate slide really for this, but that's because hand separation is simple. When something like in our salad here is undesirable, let's say you have a business meeting and you don't want to eat any onions or anything that's going to give you the bad breath, which may offend people in your meeting, because they are large enough, you can go in and just pick them out. So hand separation works when you have things that are large like that. You can pick and choose, kind of like you did in the biology beaks of finches lab, and separate and purify your mixture. Next up is filtration. Filtration is a process that separates an insoluble solid substance from a liquid, usually water, by passing that mixture through a filter. And it leverages the technique of particle size. You guys use filters all the time in the kitchen, and what we see here is a colander which is being used to separate pasta from the boiling water that it was cooked in. The way that this works is you see these holes that are here? These holes are large enough to let the water particles through, but too small to let the ZD particles through. So what happens is you lose the water and you purify the pasta. The same can be true in a chemistry class. More often than not, we will use filters that are created by using something called filter paper, and I'll talk about that in a second. What we find is that when you have a mixture like this, these larger particles that are here, when you pour out your liquid components of the mixture, your solid parts that are big get trapped in the filter, and then the stuff that can go through the filter paper comes out. Now, why can the top part here we see go through the filter paper, yet the bottom part can't? Well, you guessed it. It's all about size. There are microscopic holes in the filter paper, and the solid particles that are there are just too big, whereas the liquid portion is small enough to go through. While we were talking about the concept of filtration, I probably should teach you guys how to make a filter, or a funnel filter as they call it. So filter paper starts its life just like this, and it looks like a round sort of circle of semi-permeable paper. Now it's semi-permeable because the microscopic holes in it are small enough to capture most solids in a suspension, but it's large enough to let most of the liquid portion of any mixture through. So let's talk a little bit about how we go about making it. We start our life, as we said, as a circle like this. First thing you do is you fold your filter paper directly in half on the equator of the filter paper. It winds up looking a little bit like number 2, which is here. Then what we do is we fold it in half again. And so we wind up having our filter look like it does in number 3. So it gives you that Pac-Man sort of look where it is now in quarters. So once it looks like this and it is in quarters, what we have to do is open up one of the little folds up on the top here that have been created as a result of the way we folded it. So this that we see here is an example of one of the folds that we're looking for. You're going to take your 2 fingers, put that in there, and then spread that open, and then place the triangular filter into the funnel. You then want to take a wash bottle and you want to spray water from the wash bottle into this to make the filter stick to the sides of the funnel. Once you have that, you can then set up a ring stand using an iron ring to place the funnel with the filter in it above an empty beaker, and then you can dump in your mixture which you wish to filter. And that's how it's done. One of the questions that I get all the time is, can I just make a filter and filter out whatever the solute is that was dissolved in water, in this case some sugar water? And the simple answer to that is no, and it has to do with the size of the particles after something has been dissolved and turned into an aqueous solution. Let's take a look at this animation here. Here we are looking at a solid crystal lattice which has these little water molecules that are sort of bopping around here, and it looks like they are attacking the lattice. Now, we are going to go into depth in this process of solvation later on when we are in the ionic bonding chapter and in solutions, but for now you just have to know that why do things dissolve? Well, because water comes in, attacks that solid lattice, and pulls the individual particles into solution. In this case, this is a salt, and the ions are getting hydrated. Now, when you want to try and filter out the aqueous solution that you've created of all these hydrated ions with these water molecules, you really can't do that, and that has to do again with size. The semi-permeable ability of the filter paper relies on the fact that there are microscopic holes that are in it. Well, since the holes are designed to usually let a liquid through, the holes are just too big, and these particles, even with the hydrated crystal, are too small to get caught up in the filter. They actually flow right through. So the important thing for you to understand is that dissolved and soluble components that are in aqueous solutions cannot be filtered. I can't say it enough. That is super important. The solution will pass right through the filter. And so in that case, if we really wanted to get sugar back from the sugar water, filtration is not the way to go with that. It would probably be a better idea to do something like evaporation. Let's click on evaporation and talk about the finer points. So because we couldn't filter out that aqueous solution, evaporating was the answer to get our solute purified. The way evaporation works is you leverage boiling point and you heat the mixture with the dissolved solute to its boiling point. In this case, it will be water. Water is a covalent solid. Write this down. Covalent compounds will usually have lower boiling points than their ionic counterparts. So in this case, if we are trying to isolate a salt from an aqueous solution, we will heat the water, which will boil at 100 degrees Celsius, 373 Kelvin. The water will evaporate, and that will leave the soluble solid behind. Now, this usually happens in a flask, in a beaker, or the item that is made for evaporation, the evaporating dish. However, you can't really fit a lot of your solution in an evaporating dish. So if you're dealing with large amounts, you usually have to use a larger piece of laboratory glassware. So in this case, we basically put that on top of a Bunsen burner on a ring stand, and the water evaporated, and our sugar crystals, which we couldn't filter out in our previous couple of slides, get left behind. Here is the setup for the use of an evaporating dish to isolate and recover a salt that's dissolved. You'll notice that we set up a ring stand, an iron ring, wire gauze, and then we set up the dish with a watch glass as a cover. You may be wondering why we would use the watch glass as a cover. Well, we use the watch glass as a cover because sometimes when you are evaporating the solvent from the solute in that solution, your solid particles actually pop up and bounce out of the evaporating dish. So the watch glass allows us to watch that whole process happen, see when it's close to being done, and not lose any of our solute particles. So you always want to use a watch glass on top of the evaporating dish, and you can see it is placed on top of that evaporating dish in a concave manner. Distillation is going to follow evaporation because they are very closely related. Whereas a solid is recovered and isolated from a mixture in evaporation, distillation recovers and purifies a liquid. So let's dive into that and talk about the way it works. So as we just said, distillation will separate mixtures of liquids. We have probably seen that somewhere along the way in the creation of alcohol and old tales of making moonshine and everything, but we're going to get to that later. Here we have a solution that was created of isopropyl alcohol and water. Now, if I wanted to recover the isopropyl alcohol, I would use distillation. This procedure is going to leverage the differences of boiling point in each liquid to achieve separation, similar to the way evaporation did, but this is specific to recover a liquid solute. Now, because in our previous slide, the salt boiled at a much higher temperature than the water left and we were left with the salt in the bottom of our beaker. Well, in a case like this, the isopropyl alcohol has a lower boiling point, which means, you guys guessed it, it has weaker intermolecular forces than my water does, and therefore the alcohol boils off at 82.5 degrees or so Celsius, whereas the water would boil at 100. If you were to heat your solution that we see here to 83 degrees, we would be driving off the alcohol and be left with the water. Here is a distillation apparatus that is used to make moonshine, and the process to make moonshine really relies on the fact that you are driving off the alcohol and purifying it from your mixture of whatever you're making in your still here, and recovering the alcohol here in this jar. Let's talk about how distillation works. Instead of a still, you are looking at a distillation apparatus in the chemistry lab, but the distillation still works the same. So if you ever decide to move somewhere and go make your own moonshine, you're going to be in business here. Let's look at this. This is our mixture, and it is in a flask. Now you will notice that the flask here has a cork in it or a rubber stopper. The reason is we don't want this gas to escape. So what we do is we put it on the ring stand, we put a Bunsen burner there, and we start to heat it. The alcohol is going to boil at a lower temperature than the water does, so the alcohol vapor starts to escape from the mixture. As the alcohol mixture escapes, it takes the shape of the container, has nowhere else to go because of the stopper here, so it takes a right turn and now enters this area of the distillation flask. Now, what's going on here is kind of neat. This is a tube within a tube. On the outside here, there is cold water. This is what's called a water jacket, and this is cold. On the inside here is the hot vaporized alcohol mixture, so it's alcohol in the gaseous state. When that tube within a tube comes in contact with the water jacket, which is cold, what we wind up having is condensation. You guys should know condensation is when you have a gas that changes phase to a liquid. So what's happening is it travels down the water jacket, the cold water here, causes the hot gas to condense, and we recapture what we call the distilled liquid, which is a purified alcohol. You can do this process multiple times on your distillate that you got as a result of your process. It is sometimes called twice distilled or 3 times distilled alcohol. Let's put it this way, it's incredibly concentrated. Be careful. So that is how distillation works with a distillation apparatus in the chemistry lab. The last method of purification and separation is chromatography, and that should look familiar to you as it was more than likely done in middle school and biology class. In biology, I think you were separating pigments from some sort of leaves or the botanist curious lab, and you also may have done it to separate the pigments that are in a black magic marker, like we see here on the right-hand side. Your textbook will tell you that chromatography is another process that's used to separate dissolved solids from a solution, and it is unlike evaporation because chromatography does not leverage boiling point differences. Instead, chromatography uses attractions. And that's big here in chemistry. It specifically uses attractions of the solutes for something called the mobile phase. Let's throw in a picture here. You will see here is our mixture that we are looking at on the bottom left-hand side. And if we were to take this mixture, put it on chromatography paper, and then put the chromatography paper in water, what you will notice is the water starts to, by capillary action, travel up the paper. Now, these components of the mixture, which are our shapes, which you see here, the square, the circle, and the large yellow circle, will start to travel with the mobile phase, assuming it is attracted to it. The more attraction for the mobile phase, which is water here in chromatography, the further up the paper you travel in a shorter amount of time. So you can see here that the yellow pigments must be seriously attracted to the water because they have separated themselves from the rest of these particles, which are probably less attracted to the mobile phase and possibly more attracted to the stationary phase, which was the paper. So that is how chromatography is used to separate components of a mixture. It's kind of like a race where faster runners separate themselves from the pack, leaving the slower runners behind, and eventually you have separation. So that is it for us in our mixture purification lesson. There was a lot here, so make sure if you do have any burning questions, you bring them to the burning questions segment tomorrow. It has been a pleasure taking you guys through this lesson. I'll see you on the flip side. Peace out.
That's all, folks.